Here are some notes that are going to cover electron configuration exceptions, some overlaps, some valence electrons, Lewis dot structures for individual elements, and shorthand notation. So one of the exceptions to know to the 1s2, 2s2 electron configuration is chromium. And here's chromium right there. There are other exceptions, and the way you can tell if an element is an exception is by looking at that very bottom number. And I'm talking in this D section here, the transition metals. If that bottom number is a 1, it means it's an exception. So if you look at that next one, that's a 1. And if you look over here, copper and silver are also ones, so they're exceptions. But the only exception I'll ask you is chromium. I guarantee you that it's going to be on a test. So if you were to write the electron configuration for chromium, chromium is number 24, so you would assume you just keep adding electrons till you add up to 24. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. But that's not what really happens. It actually is this. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. So what happened? One of these electrons there in the 2 was transitioned, that's why these are the transition metals, to the D area such that it became a 5, and that dropped down to a 1. Now, why in the world would it do this? They believe they do it because of stability, but another way to look at it is writing its orbital diagram, and by diagram I mean drawing the arrows. And I am just going to stick with the 4s part, because I'm not going to have enough space on here. So 4s would have one line, because it has one orbital. And then the 3d, d's always have 5, so 1, 2, 3, 4, 5. So you would think that it's a 2 and then a 1, 2, 3, 4. You have to spread your electrons out. But what happens is that this electron, maybe it's that one over there, it doesn't matter, but one of these is moved way out there or transitioned such that it looks like this. And that would be a 4s superscript 1 and a 3d5. Now, what's a question I might ask you about this? I might ask you, how many unpaired electrons are there in chromium? So you'd have to remember that it's an exception, and then it pulls the electron from here and puts it out there. And so how many unpaired electrons total? 1, 2, 3, 4, 5, 6 unpaired electrons. Again, they think that this probably happens for stability. Each of the electrons do repel one another, and if they're each in their own bus seat, their repelling is probably reduced a little bit. Valence electrons. Valence electrons, these are the electrons in the outermost principal energy levels. They're always the S and P. They are never another sublevel, so they're not D's or F's. Always add up to a maximum of 8 or less. So the most valence electrons you could have are 8 or less. So for example, write the full electron configuration for fluorine, the valence electron configuration, and the number of valence electrons. So let's do fluorine. So my friend fluorine is right there. It's number 9. So it'd be 1, S, 2, 2, S, 2, 2, P, and I'm just counting 1, 2, 3, 4, 5. I like to count on the periodic table, so it looks like a 2P5, just like a map where you find something with coordinates. So it's a 2P5. So it said write the full electron configuration for F. The valence configuration. So the valence configuration are the outermost parts of the configuration, meaning the ones with the largest coefficient type numbers. So the valence configuration is this part. I could see a 1 there, but these two 2's trump it. So the valence configuration is 2, S, 2, and a 2P5. And from that, we can get the number of valence electrons. So we just add up 2 plus 5, and that gives us 7. Well, there's a way you can take a shortcut. And we'll look over here. If you use this side of the periodic table, because it's my favorite side, and you look at the bottom number in the upper right-hand corner, it's really hard to see on here, but it says a 7. So fluorine has a 7. And in fact, everything underneath fluorine has 7 valence electrons. That's why it's called group 7A, because it means that 7 represents 7 valence electrons. And it follows likewise. Everything underneath oxygen has 6 valence electrons, and that bottom number in the upper right-hand corner should be 6. And these have a valence of 5, 4, 3. Again, we skip these Ds. That one has a valence of 2, and that one has a valence of 1. We missed out on our friends, the noble gases. The noble gases are called group 8 because they have 8 valence electrons. Sometimes it's called group 0 because it doesn't gain or lose electrons, 0 gaining or losing of electrons. So again, you could kind of take a shortcut to find the number of valence electrons by looking at that very bottom number on the right-hand side. Now, what's interesting is if you look at the transition metals, because you can have no Ds or Fs being the valence electrons. And so if you look at these, most of them are 2s. So most of them are 2s, except for our exceptions like chromium and these ones over here. And the reason they are 2s is because their outer configuration, for the most part, would be 4s2, then a 3d something. Well, 4 in this sense trumps this d, and so you would really just have those 2 valence electrons. And so notice in this row, I know this is the 4 Ds, but these 5 S's are actually bigger, so you'd have 5s2, and that 2 trumps those Ds. So again, most of these have a valence of 2. And it goes 3, 4, 5, 6, 7, 8, and that's the 1 and that's the 2, and we just don't really give a rip about those. So more valence practice. Write the valence configuration and the number of valence electrons for the following. So nitrogen. So there's my friend nitrogen. The valence configuration is going to be 1s2, 2s2, I got to end on a 2p3, 2p3. Aha, so that's the full configuration. The valence configuration is 2s2 and 2p3, because we don't use that part. We use the outermost part, the 2s. So the number of valence electrons, so 2 plus 3 is 5. Let's check this chart. And if you look at that bottom number, it's 5. And if you look at the group number, it's 5. So it's 5 valence electrons. Magnesium. So there's magnesium. Magnesium is in the 3s range, and its outermost configuration is 3s2, because those ones before it are going to be 2s and 1s, as in 1s2, 2s2, and 2p. So the 3 trumps it. It has 2 valence electrons. You could look over here and confirm it. Yep, 2 valence electrons. Chromium. So chromium's our stinker. It is the exception. So chromium ends in a 4s1 and a 3d5. I always remember it ends in 4s1 and a 3d5. Don't you like my mouse drawing? It's so amazing. So 3 is less than 4, so really your valence configuration is 4s1, and chromium has 1 valence electron. I know it has more unpaired electrons, but its outermost electron is in the 4s, and there's 1 of them. So Lewis dot diagrams, you probably learned this in biology. It follows the octet rule. The octet rule states that nonmetal atoms want to be surrounded by 8 valence electrons. A Lewis dot diagram is the element symbol with dots surrounding it that represent the number of valence electrons, hence dot, Lewis dot. Duh. There are a maximum of 8 dots. You probably learned a very particular way to do it in biology. So if we were to have hydrogen, I would look at hydrogen and find its valence electron is 1, so we have 1 dot. And I should say, like, if this is generic element X, and if it were to have 8 dots, you can have only 2 on each side. Don't put 3 on each side, and I don't care which order you fill them up in. Generally, they like to be spaced out by themselves before they pair up, but I'm not going to mark you wrong for that. So lithium, there's lithium. It has 1 valence electron. Notice everything under hydrogen has 1 valence electron. Magnesium is 2 over, so it has 2 valence electrons. You could draw them on the north and the south, or the east and the west. I believe calcium is the exact same thing. I'm just going to draw them here. Fluorine, however, if you look at fluorine, it is way over, and it has 7. 1, 2, 3, 4, 5, 6, 7. And chlorine is underneath fluorine, so it also has 7. 1, 2, 3, 4, 5, 6, 7. It didn't really matter where I put them. This one should be closer, but, you know, it's not all working out for me. So the periodic table is a lot like a map. And I don't know if I care for this one. So I might ask you, what element is 5p5? Well, you just look, you can go from the right or you can go from the left, and then you find the p part, and there it is. 5p5 is iodine. Also, name the following element or elements. So period 2, 3 valence electrons. So period 2, it has 3 valence electrons. That one has 1, that one has 2, that one has 3. So it must be boron. So that first one is my friend boron. A great time. Next one is period 4, 8 valence electrons. Period 4, 1, 2, skip those, 3, 4, 5, 6, 7, 8. It must be krypton. The next one, name the elements with the following endings. So 2s2. 2s2 is beryllium. Next one is 6p3. Find the 6. Go to your p's and count 1, 2, 3. It's bismuth, as in Pepto-Bismol bismuth. And the last one's 3d5. Oh boy, there's 3, but there's no D's there. So here are the 3 D's. So count over 5. 1, 2, 3, 4. It's manganese. It must be for men. Shorthand notation. So find the element on the periodic table. So clearly there has to be something short about all this electron configuration stuff. So find the element you want on the periodic table. Locate and place the nearest noble gas going backwards on the table in brackets, then write the configuration starting after that noble gas. It always starts in the next period with the letter S. So let's try chlorine. Let's say I asked you to write the shorthand for chlorine. So you go up and over, and the closest noble gas is my friend neon, and you write neon in these lovely brackets that I'm not writing so well here. And then you go for chlorine, you follow it. Oh my gosh. You follow it all the way straight over to there. So it starts with 3, and all of them start with S. So a 3S, and I just look at this, it goes 3S1, 3S2. In fact, now I stop here and do a little check. Neon is number 10, correct? It is. So that means it has 10 electrons. So I have to do some adding. This happens in my head or on scratch paper. It doesn't happen on my actual turn-in paper. 10 electrons, and I added 2 with this one. And I have to add up to, I said chlorine, I have to add up to 17. My goal is 17 out here. So this has to add up to 17. So after 3S, I go empty space, and then I start here with the 3 P's. And I'm going to count over my P's. 1, 2, 3, 4, 5. 3p5. So I have 10 electrons from there, 2 from there, and 5 from there. 10 plus 2 plus 5 equals 17. So this is the shorthand for chlorine. Neon in brackets, 3s2, 3p5. Okay, we got to do another one of these. I feel it in your bones. Let's do barium. Talking about bones and chemistry teachers that are on the brink. So barium. We go up, and we go all the way over and find the closest noble gas, which is my friend xenon. So we do a lovely bracket, we do a capital X, nice little E. It always has to be that. I didn't make this notation up. And then we find barium, and we go this way. It starts with a 6, always starts with an S. In fact, you could cheat. This one ends in 6s2. And now we can check our work. Xenon has 54 electrons. And then we just added 2, so 54 plus 2 equals 56. And is barium number 56? It is number 56. I bet you want one more of these creatures from Schmanichers. Let's pick a nasty one. Let's pick beryllium. So beryllium, you go up and over. That's the easy part, and that's krypton. And I can tell already that there's some cues kind of. If you're further down on the periodic table, it means you're adding some like these 4 Ds and these Fs, which are confusing, which I have to use my squiggly chart for. And I don't have one in front of me. This may be tough. So beryllium, I have krypton in brackets, and krypton has 36 electrons, so I'm keeping track here. And now I'm going to do what I end with. Beryllium has to end in a 5p4 somewhere out here. That's my very last one. And now I'm going to put my starting blocks in. I'm going to start out at 5s. And since I'm starting at 5s and ending at 5p, all the ones in between are going to be filled. So 5s2. This is where you want to get out your squiggly chart. Otherwise, you're going to get it all wrong. So after 5s comes 4d. And you could kind of see if you go through those 5s's, then you do hit that 4d. I may not have enough space in here. And d's can hold a max of 10. Now, does that add up to 52? So 36 plus 2 is 38, plus 10 is 48, 49, 50, 51, 52. It did add up. Good golly, Miss Molly. So the 36 plus the 2 plus the 10 plus the 4 added up to 52. So we were good. And I just went to my squiggly chart to get this one. So krypton 5s2, 4d, 10, 5p4. I think we're done. Haha, these are examples of shorthands, which I've been doing. And next time we'll look at periodic trends. Ciao.